So the initial slides are kind of an overview. Dr. Panda has gone over it, Javi has gone over it, so I don't think I want to bore you guys with that. So as you know, there is a different kind of like programming models. You have shared memory, distributed message passing, logical shared memory, all that jazz. And there are several challenges that are required to be addressed if you want to support programming models for multi-petaflop and emerging exaflop systems for these kind of let's say programming models and paradigms. So you have like challenges in how do you design point-to-point communication protocol, collective communication, how do you challenge, like address energy awareness, synchronization and logs, I/O file systems, fault tolerance, etc. So going forward, we'll try to see how MVAPICH addresses these challenges and what are the designs that we have done, how do you tweak those designs, how do you tune those designs, how do you take advantage of those designs for your cluster, for your applications. So in this talk or tutorial, whatever you want to call it, so we'll be discussing about the challenges in addressing scalability for like highly efficient internode and intranode point-to-point communication, challenges in designing scalable collective communication operations, challenges in multi-threading support, like in introducing support for GPUs, accelerators, fault tolerance, resiliency, quality of service, and support for other programming models. So, and all of you know about MVAPICH, so I'm not going to go over the slide again. This is the overall architecture of the MVAPICH2 software family. So we support message passing, the PGAS models, as well as hybrid MPI plus PGAS models. And these are the various designs that we have done inside MVAPICH2 to deliver high performance to all of these higher level programming models. And these designs use different support from modern networking and multi/many core architectures. And the bottom portion of the slide lists the various technologies in terms of transfer protocols, advanced features for intranode as well as internode communication. Now we have a very strong procedure for design, development and release. Now let's say this is one thing that Carl had brought out in his talk. So unlike other libraries, when we make an alpha or beta release, that's extremely stable. So yeah, you can even take advantage of the alpha and beta releases on your systems to take like numbers, performance results, etc. We go through a rigorous Q&A procedure before making each release, which includes exhaustive unit testing, various systems level testing on large scale on multiple HPC systems, performance tuning, application based evaluations, etc. So having gone through that initial very high level overview, let's go into some of the details or let's say features offered by our several software families like MVAPICH2, MVAPICH2X, which is meant for the MPI+X or PGAS programming models, MVAPICH2 GDR, which is meant for the GPU or NVIDIA GPU accelerated clusters, MVAPICH2 Mic, which is meant for the KNCs and the upcoming KNL architectures from Intel, MVAPICH2 Word, which Dr. Giavi Lu talked about in the previous talk, so I won't go much about that here. We'll also discuss the energy aware solutions that we have in MVAPICH2 EA. And finally, we'll talk about the network analysis and monitoring, which is part of INAM. So this is the like feature list of MVAPICH 2.3b, which was released last week. Now we'll go over some key points that MVAPICH2 offers. So this is basically that. So job startup, point-to-point communication. So just like in the Ethernet world, and you have TCP and UDP. On the InfiniBand world, you have different types of transport protocols. So we'll discuss what all transport protocols MVAPICH2 supports. We'll discuss how to take advantage of multiple InfiniBand HCAs inside MVAPICH2 to deliver best performance. We'll discuss the impact of process mapping, as Dr. Hyun-Ryu mentioned in his slide. If you have bad process mapping, you can get very bad performance at application level. So we have several designs for good intranode process mapping. We have lots of enhancements to collectives in terms of offloading collective support to the network, to the HCA, taking advantage of novel switch features like sharp or multicast, designing shared memory aware or contention aware collectives for modern many core systems. And finally, we also have support for MPIT, which is a work with our colleagues from the University of Oregon. So here we are trying to see how an MPI library like MVAPICH2 and a performance monitoring system like Tau can interact with each other to deliver insights into application performance to the end users. So just like with a car, as with an MPI library, the first and foremost thing you need is for the car or the library to start up quickly. You may have a Lamborghini or a Ferrari, but if it takes 15 minutes to start up every time you turn the key, then nobody is really going to want the car. Same is the case with an MPI library. If you want to launch a job which maybe takes a few minutes or tens of minutes on a full system scale or a large supercomputing system or even one node, if it takes 15 or 20 minutes to start up, then nobody is going to use that MPI library. So the first thing that you need from a parallel programming middleware like MVAPICH2 is to get your job running fast. So MVAPICH2 has done a lot of work in this area to, one, increase the job startup as well as reduce the memory utilization required for connection setup significantly. So through our designs, we have been able to see up to 10 to 30x improvement in startup time for MPI as well as PGAS programming models like OpenSHMEM at very large core counts. We have been able to reduce the memory consumption for storing remote endpoint information. And we have actually been able to save about 1 GB per memory per node when you go to very, very large scales. And this is a number that Dr. Panda showed yesterday. So imagine if you are running on Stampere and if your job took more than like 3 or 4 minutes to launch. Most people would think that the job hung and they would quit the job and go. So these are the kind of benefits that you can get if you are using the right MPI library and the right communication mechanisms as far as something as simple as a job startup goes. Now, we have also designed a lot of enhancements to the job startup or process management interface, or PMI as it's called. So we have tried to take the PMI communication, go over shared memory so that you can significantly increase the performance of one PMI get operation. And by making sure that the data is in shared memory, we can also get significant improvements in the memory usage for storing remote EP information, as the graph on the right hand side shows. Now, we also have improved the connection establishment mechanism for PGAS programming models like OpenSHMEM. So we have done a lot of enhancements here. So we have tried to introduce on-demand connection setup mechanisms for OpenSHMEM, and as a result of the enhancements, we have been able to significantly reduce the initialization time from close to a couple of minutes to near constant at maybe a couple of seconds. So there is a significant improvement in overall job startup time, and these have been done because we have been able to understand where the bottlenecks are and come up with innovative and novel solutions to address these challenges by avoiding them or completely eliminating them. And these solutions are available in the released versions. So most of the talk is going to be like this. We'll try to introduce a feature, explain why we introduced that feature, show some performance numbers, and tell you how you can take advantage of this feature. So there'll be a slide like this saying what all environment variables you need to set, how you need to configure MVAPICH2, what all needs to be done. Say for instance, if you need to apply a patch or set a bunch of environment variables. So all of that will be listed in the slide so that this can be used as a reference manual even after the talk for you to refer back. Let's say after going back to your home institutions, you want to try MVAPICH and you want to see how this particular optimization works or how that particular design is enabled, you can use this slide as a guide. Of course, we have a user guide, but that's almost 100 pages long and it has about 400 odd environment variables in there. So it's very hard to see which variable is being used for what particular feature. So in that regard, we are hoping that this tutorial will be kind of a let's say quick start guide for you to see how to get the best performance from MVAPICH2. Now, the 22 second or let's say 5 second or 51 second number you saw here was obtained as a result of tuning a lot of these variables. So for instance, the empty degree, this variable had a significant impact on reducing the startup time from the 51 seconds that's listed here to about 22 odd seconds. So this degree determines the degree of the job launch tree for MPR and RSH. So similarly, there are lots of performance tuning options here that you can try to do on your own systems to see what performs best. So give these variables a shot if you end up having like say job startup issues on your cluster, and see if any of these variables do help. Now, once you have started up your job, you need to ensure that you have good internode and intranode communication performance. Now, if you take a look at it, most MPI libraries have two common communication protocols: eager communication protocol for small messages and rendezvous communication protocol to transfer large messages. There is always a switchover point between the eager threshold and the rendezvous threshold. Historically, the switchover point has been determined by figuring out the sweet spot between where you get the best performance and the least memory overhead. So typically how an eager protocol works is that when you post the MPI operation, the data is staged into an internal MPI communication buffer so that the application buffer can be reused almost immediately. Now this internal MPI communication buffer is used to post the data to the InfiniBand HCA. The HCA then asynchronously copies the data from it and transmits it to the remote host. Now, to store these messages internally, you need a lot of internal communication buffers, and the sweet spot that is determined is based on the size of these internal communication buffers. For most modern HPC systems, this sweet spot is around 16K. That's what we have seen. Yes?
Have you looked at what happens for intermediate data points?
As in?
Like 16K plus 1.
So typically what we do is, even though I say 16K, there is a small offset that is given. So we give about 16K plus another 1K. So like 17K is around the ballpark that we place. But for applications which use maybe 17K plus 1 or 18K plus 1, what do you do? And what is the real benefit of that? Now, let's say, and I'll like go to that point in the next slide. Now, around 16K and 17K, if you are progressing the communication frequently enough, it really doesn't matter if you are using your eager protocol or your rendezvous protocol. Now, the reason why we don't do rendezvous protocol for very small messages is because for a rendezvous protocol, there are a lot of extra, let's say, control packets being exchanged. So the size of the internal communication buffers allocated is equivalent to the size of your eager threshold, which means that if you receive a message which is greater than the size of your eager threshold, you cannot internally buffer it. You need an application buffer to receive that data. So that is where the requirement for the rendezvous protocol comes in. And as long as both processes are in the MPI library frequently enough, once you cross this point, whether you're using the eager protocol or rendezvous protocol doesn't really affect your communication performance much. But it significantly affects the amount of overlap that you can get. So that is what I would like to focus on in the next two slides. So how do you analyze the overlap potential of your eager protocol versus your rendezvous protocol? So how does your eager protocol really work? Now, the application may be doing some computation operation, and after the computation, your sender process may schedule a send operation and the receiver may schedule a receive operation. So if it is an eager transfer, because the entire buffer is already inside the MPI library and the library knows that there is enough buffer space on the receiver side to receive all of this data in one shot, the job of progressing the communication in the background can be completely handed over to the InfiniBand HCA, which means that as soon as the MPI the control comes back to the application is free to progress its computation while communication happens in the background. So one of the major benefits of this approach is that you get very good overlap of computation and communication, which results in better overall application performance. If your application is written so as to use your non-blocking operations and let's say overlap that with computation in the foreground. But one of the problems is, as Tracy mentioned, what do you do for those intermediate message sizes? So if your eager buffer size is 16K, and if you have a message size of 17K, what do you do? Or 17K plus 1 or 17K plus 2, what do you do in that scenario? Can we have an adaptive scheme which figures out what the actual communication requirement is? Now, the other option is, okay, why don't I have a very large eager buffer size? Okay, why don't I have an eager buffer size of 1 megabyte? So the problem there is, if you push up your eager threshold to a very large value, as you see here, it negatively affects your message throughput. So on this graph, we look at the impact of eager threshold size and consequently your internal communication buffer size on your message throughput. So as you can see, as your communication buffer size increases, your message throughput actually takes a big nosedive. So if you simply change your eager threshold and your internal communication buffer size without knowing what your actual communication pattern is, you get significant degradation in performance. So how about your rendezvous protocol? So typically what happens in your rendezvous protocol is, the application will schedule a communication, and when the communication happens, you just send out a ready to send message. The reason that a handshake is required is that both processes know that the receiver does not have a buffer which is large enough to receive the data. So there are no pre-posted buffers large enough to receive a data that is greater than your eager threshold size. So that is why like a rendezvous handshake is required. But the problem here is, when the RTS arrives, the receiver process may not actually be inside the MPI library to progress the communication. So you have your oops moment here. So what happens is, the application writer might have written the application assuming I have great potential for overlap, but because of the internals of the MPI library, the application developer is actually getting zero overlap here, which means that almost all of your data transfer is going to happen when the MPI process enter the wait operation. So this results in close to zero overlap for your application. So even though your application developer was very smart and tried to write the application in a smart way, because of the way the MPI library is behaving, he's actually getting no overlap at all. Now, the benefit of this is, because we are not pushing up the eager buffer size indefinitely, it has reduced buffer requirements, and it has good communication performance if used for large message sizes and if the communication library is progressed frequently. However, there is very poor overlap of communication and computation. So what MVAPICH2 proposes is to see if we can have a dynamic and adaptive point-to-point communication mechanism which adapts itself to the communication requirements of the application. Yes?
Sorry, could you just go back to the previous slide?
Sure.
So here you're assuming that the receive is a non-blocking receive, right?
Yes, because we are analyzing the overlap potential. So anybody who wants overlap should be smart enough to write an iReceive, not a receive.
I see.
So if you have a receive, then by default you're always progressing.
I see. So the receiving process essentially goes to an iReceive there,
Mhm.
but it needs to be inside the API library for the communication to complete. Is that right?
It is not that the application process needs to be inside the MPI library for the communication to complete. The communication needs to be progressed. So the communication is not completely asynchronous. The receiver process has to be actively involved in the communication to realize that the RTS has arrived, respond back with the CTS, and the sender process at that time has to be inside the communication library to respond back as well. So there is a lot of, let's say, application-driven or let's say process-driven progress that is taking place. So that is what needs to happen. Yes?
Based on the message size, we are choosing whether it's eager or is rendezvous.
Correct?
So instead, if you can go the other way, based on eager message, eager threshold, can we chunk the messages so that messages can, whatever may be that it says it can chunk, obviously send they are eager protocol.
Yes. So that protocol in MVAPICH2, so like the question is, instead of sending out a message in one shot, can be chunked out into sizes of eager threshold and sent out. Yes, you can do that. But the problem is, if you have an application which is progressing the communication frequently, then that is going to lead to very bad performance. So MVAPICH2 has an environment variable called mv2_rndv_protocol. So log on to OVENS or whatever supercomputing system you have access to, run OSU bandwidth or bidirectional bandwidth after setting Rendezvous protocol to R3. Okay, that is the chunking scheme, and to default, which is basically the RDMA based scheme. You will see that the basic RDMA or default RDMA based scheme has significantly better communication performance than the R3 scheme. Okay, so there is always a cost involved. Okay, so that is the basic difference. Is that clear? Okay. So what we are trying to say is, can we do this thing in an adaptive fashion? So can we figure out if an application really needs overlap? And if the application needs overlap, what pair of processes need this overlap? And can we just move up the eager threshold for those pair of processes? Now, the default scheme where you have like a small eager threshold which is tuned for best performance results in poor overlap, but the benefit is that it has low memory requirement. So this is what we like to call as the low performance and high productivity method. Of course, you can manually tune it by pushing up the eager threshold and the internal buffer size to a large value. This has good overlap, but it has a lot of memory requirement. So this is high performance, and because this has to be done manually each and every time, and for each and every communicating process pair, this has very low productivity. So the proposed dynamic and adaptive scheme, because it automatically figures out what is the optimal size, and it automatically figures out whether we need overlap based on profiling of internal communication requests, gets good overlap and optimal memory requirement. So this we would like to call high performance, and because the application developer does not have to do anything, high productivity. So these are the numbers that we got with the AMBER molecular dynamics application with the proposed scheme, which is in blue, and the manually tuned and the default versions. And as you can see, we get pretty good improvements in application performance while ensuring that your memory footprint is kind of on the lower side. So this is what we refer to as the dynamic and adaptive point-to-point communication protocols in MPI, and this would be coming up hopefully as in the MVAPICH2 RC1 2.3 RC1 release. So I'll skip over the tag matching because Dr. Panda already referred to that in his talk earlier. So these are some intra-node point-to-point performance numbers we get with our communication schemes on the ARM systems. So here we compare MVAPICH2 and OpenMPI, and as you can see, we get pretty good performance with MVAPICH2 for small and large messages for bandwidth and latency when compared to the latest stable version of OpenMPI. So let's move on to the kind of transport types that MVAPICH2 supports. So MVAPICH2 has support for a lot of different transport types. RC or reliable connected, which is equivalent to your TCP/IP. UD or unreliable datagram, which is equivalent to UDP. There is a mode called XRC, which is an extended version of the reliable transport protocol. And there's a hybrid version where all of these things can work together. So the benefit of RC is that you get very good communication performance, and it supports all the features that InfiniBand is known for. Let's say RDMA, atomics, one-sided operations, and all that jazz. UD on the other hand has much better scalability and much lower overhead compared to RC. However, it does not support the high-end features of RC like RDMA or atomics. So the challenge here is to see if we can have the best of both worlds. Can we have the high-end features that RC provides with the scalability that UD has? So that's where we try to come up with the hybrid communication channel in MVAPICH2, where we use a hybrid of UD and RC communication protocols for different communications. And these are the environment variables that control the use of this hybrid communication protocol. And this is the environment variables that you can use at the configure time and runtime to enable this particular feature. And as you can see, the UD or the hybrid transfer protocol gives you significant performance benefits at the application level over RC. Now, later we have a different section called the best practices section, where we have taken different applications to see what kind of tuning can be done at the application level to gain best performance, and the hybrid mode will again feature there. Basically, the choice of transport protocol significantly affects your communication performance. So that will again show up later in the best practices section. So this is something that I would strongly recommend you keep in mind if you are looking to gain the best kind of performance from your MPI libraries. Direct Connect is a new transport protocol that Mellanox has introduced. So this is again meant to combine the best of both worlds. So this gives you the high-end performance of RC with the scalability of UD. So this has a constant connection cost and the full feature set that is RDM and atomics. So this is meant to kind of let's say be the next transport protocol going forward for InfiniBand, and this is the reason why it is being projected as such. So it gives you very low memory footprint for your connection related memory compared to RC, UD or XRC that we saw in the previous slide. It also gives you very good communication performance compared to all the other transport protocols for real applications at scale. So going forward, this is being touted as the go-to transport protocol for large-scale and exascale systems. So you would have seen Craig Tierney from NVIDIA talk about multi-rail and the impact multi-rail has on let's say applications like HPL and the need for using multiple HCAs, even though it comes at a cost on modern HPC systems. So MVAPICH2 has had a lot of support for using multiple rails since the last 10 years or more. So we have schemes called rail binding, where processes are forced to use just one particular HCA, or rail sharing, where processes stripe data across multiple HCAs. And we have different ways in which we can map the processes onto the rails. We can either like have them use the HCAs in a bunch fashion, or it can be in a round robin fashion, or we can say that under rail sharing, use like a round robin fashion for small messages and striping for large messages. So there is a lot of options that MVAPICH2 has to stripe your data across multiple HCAs, or basically use multiple HCAs on the system. Yes. Okay, sure. And these are the kind of benefits that you get by using all available HCAs on a system as expected. You see a pretty good bump in bandwidth as well as a pretty decent bump in your message rate. And by using advanced multi-rail tuning options, you can even get slightly improved performance. So by default, our option is a bunch. But if you choose like a scatter option, you can see that you can get a small performance bunch, like jump over the bunch option. And as I mentioned, these are the environment variables that you can use to choose the kind of HCA you have, choose the kind of port in the HCA you use, define the kind of large message like striping threshold you have, what is the rail sharing policy, what is the process to rail mapping. So just like in the case of mapping processes to cores, so as you saw from Dr. Hyun-Ryu's talk, it is very important to map a process to specific cores. So just like that, it is also very important to make sure that the processes are using, in case of multi-rail scenario, processes are using HCAs which are closest to them. So if you have two sockets and like one HCA per socket, you want to make sure that the traffic does not go over the QPI to reach the HCA. So the process to rail mapping is extremely important, especially if you are using accelerator based systems. So this is because of the platform limitations and the fact that advanced techniques like GPU direct RDMA or GDR copy, which are very commonly used for GPU enabled applications using MVAPICH2 GDR, does not work across a QPI. So the process to rail mapping is extremely important for either host based or GPU based applications. If the process-to-rail mapping is incorrect, or if the processes end up using the incorrect HCAs, you would get very, very bad performance at the application level or even the macro benchmark level. Yes?
So these are environment variables, right?
Yes.
So currently does MVAPICH have support for figuring out what the right process is?
As in?
Does MVAPICH automatically do this?
Yes.
Automatically rectifying the optimal?
Yes.
Okay.
So HWLock has a feature which tells each process what is the closest HCA to it. So we use that feature to make sure that the HCA selected by a process is the one closest to it. This is extremely critical for MVAPICH2 GDR, even more so than the basic MVAPICH2. So for the basic MVAPICH2, if you end up using the wrong HCA, you might see maybe like 3 to 7% degradation. That's about it. But if you end up using the wrong HCA for MVAPICH2 GDR, you might end up getting 2x to 4x times the degradation, or even more than that.
I see. So related question. So then why would you expose these environment variables? Because it's already SHA solved all, right?
So the thing is, users could have different kind of HCAs. So we don't have access to all sorts of systems and all sorts of configurations in the world. So we want to make sure that users are aware of these things, so that in case they end up with a system where you have a different kind of mapping, or like if things don't work in the default configuration, we want them to be able to play with the settings and let's move things around to make sure that it works for them. So we want to give the users as much flexibility as possible. That is a goal.
What happens if there are multiple HCAs on different nodes, and in the same node, some of which are configured for Ethernet and some of which are configured for Infinity?
So MVAPICH does not work with Ethernet at this point in time. MVAPICH2 only works with InfiniBand. So again, when you say Ethernet, do you mean the network Ethernet, or the endpoint is exposed as an Ethernet endpoint?
The switch through which the port is connected is configured as an Ethernet switch.
Okay, so if your endpoint is a Mellanox IP HCA configured in Rocky mode, MVAPICH2 will still work over that. However, if you have one Rocky HCA and one InfiniBand HCA, MVAPICH2 will not work in that configuration. That will be like a failure case. So that's something that still needs to be handled. And the other case that you talked about is like a heterogeneous configuration. One node having 3 HCAs, the other node having 2 HCAs. That is a work in progress. So hopefully with the RC1 release, that configuration will work. I wanted to make that work with 2.3b, but I couldn't push in the feature soon enough. Any other questions? Okay. So going forward, this is again going back to what Dr. Hyun Ryu mentioned. Process mapping is extremely critical for high performance MPI libraries, especially on emerging like Knight's Landing systems or the dense many core systems where people may end up using more of an MPI plus OpenMP paradigm. So for this particular reason, apart from the default bunch and scatter mapping schemes, we have recently introduced what is called a hybrid process mapping scheme for MPI plus OpenMP kind of applications. And MVAPICH2 has different kind of binding policies. So we have certain preset binding policies, and we also have user-defined binding policies. So just like we have this environment variable process-to-rail mapping, which can say make process 1 use HCA1 or process 2 use HCA2, so on and so forth. We have a lot of like binding policies to say that process 1 should get bound onto core 1, process 2 should get bound onto core 10, so on and so forth. So the binding policy can either be user defined, where user can have maximum flexibility in where the processes get bound to, or users can use one of the preset binding policies like bunch and scatter and the newly introduced hybrid. So let's see what these binding policies are. Now the default binding policy is at a core level and a bunch mapping. So if your computer device looks like this, a core level bunch mapping policy will result in the, let's say if you have 4 ranks, the ranks being mapped onto socket 0 in like a serial fashion. If you have a socket or Newman node level binding policy, with bunch mapping, then MVAPICH2 will guarantee that all the 4 ranks gets bound onto socket 0, but they are free to move within all cores available on socket 0. So that is the flexibility that the NUMA node or socket level binding gives over the core level binding. The core level binding mandates that a rank is always bound to one core, whereas a socket level binding only guarantees that a rank is bound to one of the cores on this socket. We also have a scatter binding policy. So if you look at bunch, you would see that all the ranks are bound down to socket 0. But if you look at scatter, you will see that it will be rank 0, then rank 1, rank 2 and rank 3. So it's kind of in a scattered fashion. So again, you have a core level and socket level binding policy. So core level guarantees that the process is bound to a particular core, whereas a socket level policy only guarantees that a process is bound to one of these sockets. Now we recently introduced process and thread binding policies in the hybrid mode. So for that you would set the binding policy as thread, and you would tell MVAPICH2 how many threads are expected per process. So let's say if you are using 4 OpenMP threads or 6 OpenMP threads, you would tell MVAPICH2 whatever number of OpenMP threads you are planning to use by setting the MV2 threads per process to that particular variable. Now we also have 2 default or preset binding policies here, which is linear or compact. Now linear binds the MPI ranks and OpenMP threads sequentially, that is one after the other, and this is recommended to be used on non-hyper-threaded systems with MPI plus OpenMP. Now compact, on the other hand, binds MPI rank to physical cores and locates the respective OpenMP threads on hardware threads which are associated with that physical core. This is recommended to be used on multi or many core systems like KNL, OpenPower. So this will be the default on these kind of systems. And this figure shows how the binding policy would work if you chose a hybrid binding policy with 4 threads per process and compact as the binding option. Now, if you have a system like this, let's say, consider that each one of these is one tile of a KNL. So you have, let's say, 1 core and 4 hardware threads associated with that core. If you have this particular setting, what would happen is that the process would get bound to core 0, and then we would reserve 3 other cores for the other OpenMP processes. So this is how your process mapping would happen in the case of using the hybrid binding policy with the compact option. Now this detects the hardware thread support in the architecture and assigns MPI ranks to physical cores appropriately. And this is the example where you chose the binding policy as linear over compact. So as you can see, there's a difference in how the processes are getting bound to the cores in both scenarios. Now, you set a particular binding policy. How do you make sure that the binding policy took effect? How do you make sure that the binding policy, whether it is from the HCA or let's say process to HCA mapping or process to CPU mapping, took effect? So we have environment variables called MV2 show CPU binding or MV2 show HCA binding, which shows which rank is bound to which let's say core, or which rank is using which HCA. So these are a couple of very useful debugging tools that you can have to see what core a particular rank is being bound to. Or there is the other variable MV2 show HCA binding instead of CPU binding, which tells you what HCA a particular process is using. So this is very useful if you are running on let's say a multi-rail system, or if you are running on a many core system and you want to ensure that your HCA mapping or your process to core mapping is working as expected. Now, as I mentioned, we have support for like enhanced collective operations, which take advantage of the multi-core aware designs for internode as well as intranode communication. So your internode communication can go over either point to point or let's say hardware offloaded mechanisms, your intra-node communication can go over either point-to-point, shared memory, or kernel-assisted modes. And these are the two environment variables you can use to enable or disable each one of these specific features. Now, hardware multicast, I think Bracy would be extremely well aware of that. I'm not sure if other people are aware of this feature. So, InfiniBand has a feature which allows you to send the same packet or replicate the same packet to different end nodes on a particular system. So, this feature is called multicast. This is available in almost all networks. So, in MVAPICH2, we use the multicast feature to implement MPI broadcast, and we also add software reliability on top of it because multicast is implemented using UD or unreliable datagram. So we want to ensure software reliability on top of that. Yes?
So this is set by default. Is set by default?
So there are two things here. Your system has to have the necessary libraries to support a multicast. If the necessary library support is detected at configuration time, then it is enabled by default at configuration time. Then to enable it at runtime, you need to set this environment variable MV2 use mcast to 1. Okay, so there are two things that are required. So there is a like a system library dependency, and if the library dependency is satisfied, then you will have to enable it at runtime by using this variable.
Okay, so related question. So is there other you see cases where MVAPICH is not able to detect this library for multicast, right? But then
No. So if the library is present, MVAPICH2 detects it at configure time. We have not seen a case where the library is present and MVAPICH2 is not able to detect it. Yes?
Will you have any question for 32 kilobytes 6K?
So this was taken at full system scale on almost full system scale on Stampede at about 4K nodes. I'm not really sure why there was a bump here. So this could have been an experimental variation or noise. Any other questions? So one of the major benefits of, by the way, this is the default host-based scheme, but if you look at the multicast-based scheme, it is more or less flat. So you don't see that variation there. So one of the major benefits of the multicast-based scheme from this graph, as you see, is its scalability. So it's kind of flat. Irrespective of the number of nodes you are running on, for a small message or a large message, the kind of performance you get is kind of constant. This is the dream of almost every MPI or application developer, where you have a really scalable collective operation which is not affected by the scale of the system on which you are running on. So we also have support for multicast based scatter, and at least for small messages we see pretty decent improvements by using the multicast enabled scatter, and the flags for enabling this are same as the flags for enabling the broadcast scheme. So we also have sharp based support for collectives. So here we show the benefits that you can have by enabling the sharp based support for small message collective operations for like 16 nodes with 4 processes per node, and for 16 nodes with 28 processes per node. This was taken on Broadwell systems with EDR, InfiniBand EDR interconnects. So you see significant improvements in performance for different kind of configurations for different message sizes on the latest kind of systems. So the benefits are not limited to micro benchmarks. You also get performance benefits at the application level. So these are the benefits you see with the HPCG high performance conjugate gradient benchmark, which is being touted as the next HPL or like a replacement to the HPL depending on whom you talk to. And also with the mini AMR or adaptive mesh refinement algorithm. So you see that we get pretty constant benefits at different scales. And just like with hardware multicast, there is a configuration time and a runtime flag that you need to use to enable this particular feature. More details of it are available in the MVAPICH2 user guide. So if your system does support these things, give it a shot. And note that this has other dependencies. You need to download the HPCX software suite from the Velonox website. Install it, and you need to start up a couple of daemons. There is a sharp daemon that needs to run on each node, and there is a sharp aggregation manager which kind of orchestrates your let's say sharp communication setup. So those two libraries needs to be installed before you can begin to use Sharp inside MVAPICH2. But if you can use it, you can see significant performance benefits. And if you go back to what Deva and Gilad had mentioned in their talks, they mentioned that Sharp is not only available for all reduce, but it's also available for other collective operations such as bcast, barrier, and reduce. So currently Sharp only supports like a subset of your math operations. It does not support all of them, but it supports the most common math operations like sum, min, max, etc., which is most commonly used by end applications. Now let me quickly touch upon non-blocking collective operations. So just like with your non-blocking point-to-point operations that we saw earlier, one of the major problems with your or the idea behind non-blocking communication, let's say the problem with blocking collectives is that again there is no overlap of computation and communication during the actual execution of the collectives. So the non-blocking collectives were introduced to have this kind of an overlap. But again, the problem, just like with your point-to-point communication, is who is going to progress your communication. Okay. So with the point-to-point communication, the MPI library had to enter the progress engine to progress the communication. So with your non-blocking collectives, the idea is, can we have a communication support entity? What that entity is can be defined later, but can we have a support entity which can progress the communication in the background while the application is doing computation in the foreground? Now, if you look at your basic point-to-point operations, there is only one communication to progress. So you don't need to enter the communication progress engine very, very frequently. Once in a while should suffice. But if you look at a collective operation, it's a series of point-to-point operations, not just one. It will be hundreds. So you will have to enter the communication progress engine very frequently. So that is why a communication support entity is more essential for collectives than it is for point-to-point. So this is how it is supposed to work in theory, but theory is almost always very different from practice. So the catch is, who is this communication support entity? Who will progress this communication? So will it be a thread? Will it be a process? Will it be a hardware resource? Can you do it without any thread or hardware resource? Can you do it using your basic, let's say, RC protocols that InfiniBand offers by default? So these are the challenges in designing non-blocking collectives. So, and this is how one would write an application with non-blocking collective operation. So you would initiate a non-blocking collective, you would do computation that does not depend on the result of this particular operation. You would periodically check for completion, you do more computation, and finally you wait for the collective operation to finish. And the hope is that the collective operation actually progresses during these computation phases, so that the amount of time you end up waiting in the final MPI wait is not very high. But again, theory is very different from practice, and it depends on how the message progression is implemented inside the MPI library. Now, if done well, this is the kind of benefits that you get. So here we look at the performance of the P3D-FFT kernel at 8K nodes on Stampede. So 8K nodes is 8K processes on Stampede. So using RDMA-aware non-blocking collective operations, we can get up to 20% improvement at 8,000 cores on large-scale supercomputing systems like Stampede. So again, as I mentioned, if done well, this is the kind of benefits you can get. If not done well, look at the blue line here. So this is a scheme where we are using a thread as a communication support entity. So MPICH or MVAPICH has a progress thread which is meant to let's say progress communication in the background. So as you can see, by enabling that extra communication support thread, you are actually screwing up your performance. The reason here is that the communication support thread is stealing CPU cycles away from your main thread and thus hurting the overall performance. So again, the choice of your communication support entity is extremely critical, and we hope that these designs will be available. Basically, the support for RDMA-aware non-blocking collectives will be available in the next release of MVAPICH2, which is RC1. The code rec based support is already available in MVAPICH2X. Now, moving on to MPI support, this what I mentioned earlier. So, the MPI tools interface was introduced to the MPI 3 standard to expose the internals of how MPI works to performance monitoring and analysis tools. So there are different kind of like variables associated with the MPI tools interface. So one is called the control variables or C bars, the other is called performance variables or P bars. Performance variables just tells you what is happening inside the MPI library, and control variables allows you to potentially modify some behavior of the MPI library. And this is how one would use the MPI-T interface. So you would get the number of variables, query the metadata, and depending on what sort of variables you want to, you would either allocate a session, interact with the control variable, finally free the session, or if it's a control variable, you would allocate a handle, make necessary modifications, and free it. Now, depending on the support, certain control variables can either be set at any point in time during the application execution, while certain variables can only be set during the or before the initialization of the MPI library. So again, that depends on the particular control variable in use, and when you query the control variable, the MPI library will tell you like what the scope is. So does this affect everything or not? Now this is a sample pseudocode of how you can optimize the eager threshold limit dynamically, and this kind of goes back to the question Bracy raised before. So what happens if by desired eager threshold is 1 byte or 1 kilobyte over what the system sets by default? So in these scenarios, with the dynamic and adaptive mechanism that was mentioned earlier, the let's say tool or the user has the flexibility to modify the eager threshold at runtime. So these are the let's say high-end features that the MPI tools interface provides performance monitoring and analysis tools or end users. And these are some examples of the kind of benefits you can get by let's say using or these are the kind of insights that users are gain into the application communication characteristics in terms of number of unexpected messages expected, or the number of intra-node and inter-node communication that happen using the MPI-T communications interface. And this is a slide again. This Dr. Panda mentioned this of how MVAPICH2 and Tau works together to expose the performance and control variables to the user in a nice like graphical user interface. And please talk to Srinivasan sitting back there if you or RL if you guys want any more details of this particular effort. Now with that, let me move on to MVAPICH2X. Before that, are there any quick questions on whatever features I had described about MVAPICH2? Okay, if not, let's move quickly on to MVAPICH2X. So MVAPICH2X supports gives support for hybrid MPI plus PGAS applications. So instead of having multiple runtimes, we can have a single unified runtime, thereby consolidating network resources as well as avoiding possible deadlocks that occur when you progress multiple communication runtimes at the same time. So MVAPICH2X gives significant performance benefits for various PGAS communication models like UPC++ and OpenSHMEM. So these are some examples of the kind of performance benefits you get with the hybrid MPI plus OpenSHMEM programming model for Graph 500 and the simple sort benchmark. And this is more of a recent work where we try to see the kind of benefits like you can get with the OpenSHMEM on the KNL architecture, which was done by Jahanzeb. And we try to compare the performance that is obtained on the KNL with and without MCD RAM as well as on Broadwell, and show the results here. So this is a work done by Mingzhe on how on-demand paging can help. So before that, what is on-demand paging? What is the requirement for on-demand paging? Now, for high-performance communication libraries like InfiniBand, there is a requirement that the memory which the IBHCA is accessing be pinned. So why is this? This is basically because when you post a send operation, you are actually giving a request to the InfiniBand HCA saying that I want you to send a message which is in this particular location out of the HCA. But this is not a synchronous operation. This could potentially be an asynchronous operation. When the IP HCA comes back and tries to go to the memory location, if the data is not there, then it is like, let's say if it gets swapped out, then you get corruption. So this is basically the reason why your memory gets pinned. But what is the con of that? If a lot of memory gets pinned this way, you are stealing that memory away from the application, which cannot use it anymore for its computation. So this is basically the reason why, or one of the reasons why Mellanox introduced this feature called on-demand paging. So on-demand paging basically allows these memory locations to be swapped out if the application so chooses. And when the IPHCA comes to access this particular piece of memory, if it is not there, there is a page fault, and the kernel brings in that particular piece of memory. But this page fault has a lot of overhead. If you keep on hitting this page fault, then the entire purpose of using InfiniBand, which is high performance, will be lost. So the challenge for MPI designers like us is to see if you can have, let's say, have the cake and eat it too, so to speak. So can we use on-demand paging and avoid pinning while avoiding the performance issues that you encounter with the page faults? So we introduced several designs for this. So this was done by our student Mingja. Unfortunately, he is not here right now. So in this graph, we try to show the kind of performance you get with the pin down scheme, which is the default scheme, your explicit ODP and your implicit ODP scheme, which are both designs inside MVAPICH2. This was done in an SE16 paper last year, and this most probably will be a high PC paper this year, which is under review. So as you can see, there is little or no degradation between your pin down schemes and the proposed on-demand paging based schemes inside MVAPICH2. But the benefit is that the on-demand paging based schemes requires no pinning of memory, thereby allowing applications to use that memory if they need it. So that flexibility is there for applications with the on-demand paging scheme. So with that, let me quickly move on to MVAPICH2 GDR, which is basically our CUDA aware MPI library, and you have been hearing about that from different people like Craig Tierney in his tutorial and his talk. So MVAPICH2 has support for like efficient small message communication with GPU direct RDMA. It also has multi-rail support and an enhanced version of it that we saw with the basic MVAPICH2. It has efficient support for intra-node communication using CUDA IPC. It has support for data types, and it has also support for triggering communication operations from the network. So if you recall Dr. Ron Brightwell's keynote talk, he mentioned triggering communication operations from accelerators as one of the requirements for, let's say, Exascale computing systems. And the work that we are doing with NVIDIA, which is called GPU Direct Async, does exactly that. Now, we have like different kind of designs for small message as well as large message transfers inside MVAPICH2 GDR. So there are two schemes. One is a loopback based scheme. The other is using the GDR copy scheme that NVIDIA and Mellanox work together to bring about. So there are several different approaches that you can take for communication here to transfer data from a host to the GPU or GPU to the host. So different designs have different bottlenecks. In MVAPICH2, we have tried to figure out what design works at what message size and pick out the best possible design for the best possible message size. So in fact, when you see these designs, you only see a smooth curve, but actually like from 0 to maybe 4 or 8 bytes, we could be using design 1, so we could be using GDR copy. Whereas from 8 bytes to about 128 bytes or so, we could be using a second scheme. And for your really large messages, we could be using completely different third scheme. So even though you see one smooth straight line, the internal designs that are being used to achieve this performance could be varied, depending on whether you are transferring the data from a host to a host, from a GPU to a GPU, from a GPU to a host, so on and so forth. So as you can see, with our latest designs, we have crossed the 2 microsecond boundary. We are actually at 1.91 microseconds to transfer data between one GPU to a GPU on a remote node. So this is a kind of performance that no other GPU aware library can offer you out there. So those numbers were on the Intel Haswell systems. So these are the numbers that we recently got on the OpenPOWER, basically NVLink plus Pascal systems. So we get extremely good communication performance for intra-socket, inter-socket. So the reason why you don't get the kind of performance benefits that you saw in the previous slide is because of a lack of GPU direct RDMA support in the OpenPOWER systems. So there are some hardware limitations which prevent us from using GDR at this point in time. But once the Power 9 systems are here, we expect these limitations to go away, and the performance should be similar or better than what you see on the current Haswell systems with Pascal GPUs. So just like with MVAPICH2, and I think Craig Tierney had highlighted some of these numbers in his or some of these environment variables in his talk as well. There are lots of environment variables that you can use to tweak these the performance. Now going back to your question, Srinivasan, so you had asked why we are exposing these things, right? So we had set these to what we thought were the best values. But Craig ended up running it on a different system with a different number of HCAs and a different GPU architecture, which we did not have access to. So if we had not provided these environment variables to him, he would not have been able to tweak it and get the kind of performance he wanted.
Yeah. So basically what I'm asking is there a tuning opportunity there?
Yes. There is always tuning opportunity, but I cannot guarantee that there you will get benefits over what we are calling. Yes, basically.
How is it that you determine what the best sizes are? That's part A. Part B is, could it be done automatically?
How do we determine what the best sizes are? So we take an algorithm, run it for all message sizes. So you get curve 1. You take the second design, run for all message sizes, you get curve 2. So there will be some intersection between curve 1 and curve 2, and we figure out which one is better and try to say, okay, from let's say message size 1 to 2, use design 1. Message size 2 to 3, use design 2, so on and so forth. It's a painstaking process. We are trying to automate that. So for collective tuning, we have a method to automate it. But for point-to-point GPU-based tuning, we still haven't automated the process. Unfortunately, it falls on the top of people like Amar and King to do this tuning, which obviously they don't like. But we end up doing that anyway. So that you get these, let's say when Dr. Panda goes to present somewhere or I go to present somewhere, we can show these very nice smooth curves without all the different bumps that we would be seeing internally. So going forward, there are lots of environment variables here. I'm not going to go over each and every one of them. Please visit the links at the bottom of these slides to get more information about these different environment variables. So every one of these things will allow you to pick a different design inside MVAPICH2 GDR or MVAPICH2. And each one of those designs might be applicable to different communication areas. So if you have the right tuning, then you can get significant performance benefits for end applications like HumDBlue on reasonably large number of nodes with MVAPICH2 GDR. And this is the kind of environment variables that we had used to get this performance benefits on different problem sizes. So let's quickly go over to the multi-rail support. So just like with MVAPICH2, you have different process to rail mappings as well as rail sharing policies. And these are the kind of benefits that you can get, and this is fairly obvious that you get much better bandwidth if you are using 2 rails as opposed to 2 HCAs as opposed to 1. So this is something fairly obvious. But one thing that I would like to highlight here is that starting a couple of revisions before, Mellanox OFED has begun to expose different ports as different HCAs. So about 2 or 3 years back, if you bought one Mellanox HCA with 2 ports, and if you did IB stat, it would show up as one HCA with 2 ports, port 1 and port 2. But starting about maybe 2 years ago, they have begun to expose this as 2 different HCAs. Okay, so if you buy one EDR HCA, install the latest Mellanox OFED on it, and if it has 2 ports, it will show up as HCA1 and HCA2. But if you try to do these kind of experiments on such systems, you will not see this huge bump in performance because your bottleneck is your PCI at that level. So your PCI can only handle so much traffic, so you will not see these kind of bumps. So that is something that you need to keep in mind when you are running experiments, because from a user's perspective, and even like you will not immediately see that they are, it's just one HCA with the two different ports. But if you do LSPCI, you will see that both have the same root number. So they, instead of showing up as PCI device 4 and 5, it might show up as 4.0.1 and 4.0.2. So that's an indicator that it is actually one device with two ports, not two separate HCAs. So just a tidbit that you need to keep in mind if you are if you end up doing tuning. We also have support for efficient intranode communication using CUDA IPC. So with multi-node configurations, typically there are multiple ways you can transfer data from one GPU to the other. So one common method is to take the data to the host memory and bring it back to the remote GPU. But this is typically not very good performance. So NVIDIA has this feature called CUDA IPC, which allows you to transfer data through the I/O hub to a remote GPU. Now this is handled by a DMA engine. It bypasses the host. It has low latency and is asynchronous. However, it requires creation and mapping of memory handles. So just like a rendezvous transfer, you need to know where you are transferring the data to on the remote side. So there is some additional overhead here. So we have advanced designs in MVAPICH2 GDR to ensure that we get the best performance for like device-to-device transfers using CUDA IPC for small or large messages. So these are the kind of various designs we have. This is the performance you get if you transfer it after staging on the host memory. This is what the performance you will get if you just do your basic IPC. And this is the performance you will get if you choose the enhanced designs that we have inside MVAPICH2 GDR, which is what we refer to as SMP IPC. And these are the environment variables that like control the like use of these different designs. So we have like a lot of different designs. So we have double buffering schemes and cache-based designs to take advantage of like all the performance that the various features can offer. And these are the environment variables that can be used to enable or disable each one of these features. So this is the benefits that you get using one of the proposed IPC cache designs. So you can see we get up to 4x improvement in performance with these support. So far we've been looking at basic point-to-point communication using simple data types, but as you know, applications use a lot of complex data types which have like structures or unions in them. So how do you take advantage of these complex data types? So for that we have built-in kernels to perform packing and unpacking of these data types, and these are the environment variables that let's say enable or disable these particular features. And this is the kind of benefits that you can get by using the proposed kernel assisted schemes for packing and unpacking over your default schemes. And the benefits are not just limited to like let's say a micro benchmark. We actually get a lot of performance benefits for real applications which are used by scientific communication scientific community, like the Cosmo weather modeling application. So you get significant benefits with our proposed designs with real applications at scale. So that's a very important benefit. Now let me quickly touch up on GDS. So as I mentioned, so typically CUDA has been treated as a second-class citizen so far. So the CPU is the master. The CPU decides when to do the communication, when to do the computation. So the CUDA is more or less a slave. The CPU tells the CUDA, okay, do this compute. And the CPU keeps on pinging the NVIDIA device to see if, hey, is the job complete? Is the job complete? Or the NVIDIA device asynchronously notifies the CPU saying that the job is complete. But the CPU is the master who is orchestrating everything. So the challenge here is And because the CPU is orchestrating all of these things, the CPU is, let's say, once the CPU does some compute, launches the kernel, all of this time the CPU has to wait to figure out if the the CUDA operation is complete. So only after the CUDA operation is complete can the CPU perform other operations. So during all of this time, the CPU is stuck doing nothing. Okay. Now, this is how a typical, let's say, CUDA-aware program or CUDA-aware application would work at this point in time. So the CPU would do some compute, launch a kernel, wait for the kernel to finish, do some communication operation, wait for the communication to finish, then do further compute. So all of this time, the CPU is actually doing nothing. So the green, the blues, and the greens are useful work, whereas the orange and the yellow is basically wasted work. So can we, let's say, remove this wasted work and replace that with useful work? So that's what GPU Direct Async is trying to do. So can we enable more asynchronous progress? So GDS aims to decouple the control flow between GPUs and CPUs. So the idea is for the CPU to say, tell the GPU that, okay, here is a kernel, you do this computation, once this computation is finished, you do a send operation. So if the CPU does all of that, then the CPU really doesn't have to wait until the kernel finishes and wait for the send operation or any of these things. So the CPU can tell the GPU device to do all of these things, so that the GPU will do the computation operation, then trigger the send operation from the GPU itself. The CPU can then just wait for a small period of time for like an acknowledgement and go on to do other useful things while the GPU waits for the communication to finish. So as you can see, this completely decouples the CPU and GPU, the control flow between them, and allows the CPU to do more productive tasks. So here what you saw was that the GPU finished another round of computation and scheduled a kernel which could then run. So the benefit here is that the kernel launch overhead is significantly hidden. So these are the kind of benefits that you get with GDS for latency oriented as well as throughput oriented kernels. So I know I'm kind of rushing through a little because I want to make sure I finish on time. We have hold you back long enough. I don't want to keep you back anymore. But before I go on to the energy aware topics, is there any questions about MVAPICH2 GDR? Okay. If not, let's go on to MVAPICH2 EA, which is basically our a white box approach to see if we can have energy efficient communication protocols for point-to-point collectives as well as RMA. And these savings, I should mention, is application oblivious. So the application need not like throttle communication explicitly. The MPI library will figure out when to throttle the communication and how to do that. And as the graph shows, we are also able to provide maximum guarantees on the kind of degradation that is acceptable. So we are able to get significant performance benefits over the pessimistic MPI. The pessimistic MPI is a version that throttles down your CPU's clock when you enter the MPI operation and throttles it back up when you exit that. So that is kind of the maximum savings you can get. So what this graph shows is that we are able to get the same kind of let's say energy savings as a pessimistic MPI while significantly performing better than the pessimistic MPI version for a wide range of applications. So the same techniques that we apply to a point-to-point and collective communication are also applicable to the RMA operations, as you can see in this graph. So we also have some energy monitoring tools which you can use as an LD preload option, which tells you how much energy was used by your DRAM, your package, your memory, your CPU, so on and so forth during the application execution. So finally, we have what is called the incident network analysis and monitoring tool, which allows you to analyze what is capable of happening in the network and correlate network traffic with like MPI and the job scheduler. So it can basically tell you how much traffic is going on a network, and of that traffic, what portion of the traffic was contributed to by a job, and within that, what portion of it was contributed to by one process, and so on and so forth. So you can drill down deep into the performance being offered by various processes on the network. So this allows you to correlate a lot of details of network traffic with how the MPI process is behaving on that network. And we also have support for OS2 microbenchmarks. So whenever we make a new feature available in the MPI library, we make sure that we release a corresponding benchmark for users to perform apples to apples comparison between different MPI libraries of that particular feature. So OMB has support for MPI and various PGAS models like UPC, UPC++, and OpenSHMEM. So we continue to add new features as and primitives as we add support for them in the MPI library, and it's also part of various procurement suites like NERSCATE, which are used by DOE and various supercomputing centers to actually buy different HPC systems. So actually, I will skip this part because we are kind of running out of time. So this is basically the applications level tuning that we have done. This shows the kind of benefits that you get at the application level with different tuning flags. So again, Srinivasan, this could be useful for you. So this kind of shows you what CVARs or environment variables you can tune to get performance for end applications. So here, in these two examples, we tuned the eager threshold and the VBUF size, the internal communication buffer size, to improve the overall application performance. So here we try to see if we can use different transport protocols to improve the application performance. So here we use the UD transport protocol over the default RC. Same in this application. And we also have a lot of benefits that come due to collective tuning to the performance of end applications. So with that, let me conclude this talk with briefly mentioning what we are looking for the future. So we would like to look at the MPI plus task-based programming model. We want to see how we can enhance tag matching and take advantage of the adaptive memory. So if you think back to Gilard's talk, so this is the blue field technology that Mellanox had mentioned. So we want to see if we can take advantage of the FPGA or the core on the HCA to do small operations. As Ron mentioned, can you do some sort of mapping small operations to improve the performance? So we also want to see how best to take advantage of the MCD RAM and the NVLink and the CAPI interconnects that are coming up in the Knights Landing and Open Power systems respectively. And some of these designs are already available in research preview versions, and they'll be made available in future releases of MVAPICH2. So with that, let me conclude the talk, and thank you for your time and patience.